Let's go back to that picture we had before where we had some fluid and we were looking at some box-like shape of the fluid. Remember, what are the forces that are acting on it? Well, we've got the weight of the fluid, the weight of whatever that box is of fluid. We've got a pressure acting on it from below, from the fluid below pushing up. We'll call that F2. The force from the water above, from the pressure above, we'll call that F1. And we know, assuming upward is positive, F2 minus F1 minus W equals 0. In other words, bringing the W to the other side, F2 minus F1 is W. Well, we can think of this in terms of W is the weight of the fluid, and then the external fluid is applying a force on this section of fluid that's opposite that weight in the upward direction. It's equal to the difference in the forces from the bottom and the top. That force acting on the fluid we call the buoyant force. It's acting on this fluid from the external fluid, pushing on this because there's a greater pressure below than there is, than there is above. We'll call that F sub B for the buoyant force. Now, let's imagine we remove that fluid and we put something else in its place. So we put maybe a block of wood or something like that in the place of that fluid. Well, this buoyant force, due to the external fluid, is going to be exactly the same whether we have water in there or some other object. There's going to be exactly the same buoyant force from the external fluid acting on that object. How much is that buoyant force? Well, it's the same as it was before. It's the weight of the original fluid. So I'm going to put this down as the weight of the fluid. Now, how much fluid? Well, if we think about taking an object and putting it in there, it's the weight of the fluid that we have displaced by putting the object there. So what we'll call this is the weight of displaced fluid. The weight of the displaced fluid. In other words, it's the weight of the fluid that would be pushed out of the way by putting this object in its place. It's how much fluid has to be removed by putting some object in under the water's surface. That is the buoyant force that's acting on the object when we put it underwater. So there's actually a force acting on the object due to the external fluid pushing it upward. That's what we'll call the buoyant force, and the buoyant force is equal to this weight of the displaced fluid. Now we can actually demonstrate that with a sample of fluid and putting some object in the water. So here I have a spring scale and a mass of aluminum. And when I put the mass of aluminum on the spring scale, we see that the reading of the scale goes down a little bit. Now what I'm going to do is I'm going to submerge this aluminum block in water, and what I want you to notice is that the reading on the scale will actually go up a little bit. In other words, the weight that we have to apply from the spring scale, the force from the spring scale, decreases because the fluid will actually apply an upward force due to the buoyant force. Okay? Here we go. I'll try and hold this as steady as possible. There we go. Did you see that decrease in the force? In other words, the reading on the spring scale goes up. That's because the buoyant force is pushing on the mass, pushing it upward, decreasing the force required by the spring scale. So let's imagine we submerge some object and we displace that water with the object. Like we take whatever this sample is and we put it in the water under the surface, completely submerged. Now, what's it going to do? What's going to happen? Well, there are two forces acting on it. The weight of the object, pulling it down, and the buoyant force, pushing it up. Now remember, the buoyant force is equal to the weight of the displaced fluid. Well, that means the weight of the displaced fluid is the mass of the displaced fluid times g, while the weight of the object is the mass of the object times g. Now remember, mass is equal to density times volume, so the mass of the displaced fluid will be the density of the fluid times the volume of the displaced fluid, but the volume of the displaced fluid is exactly the same as the volume of the object. So this will be the density of the fluid times the volume of the object times g. While the mass of the object will be the density of the object times the volume of the object, and then times g. Now, which one of these is bigger? Is this quantity bigger, or is this quantity bigger? Well, it will completely depend on the density of the fluid compared to the density of the object. If the density of the object is larger than the density of the fluid, then this force will be larger than that one, and the object will sink. However, if the density of the fluid is larger than the density of the object, this force will be larger than this one, and the object will rise. If they are exactly the same, the forces will be exactly the same, and the object will stay exactly where it is. So, by comparing the density of an object to the density of the fluid that it's in, that will determine whether the object sinks, rises, or stays where it is. Well, let's look at an example. Have you ever seen an ice cube in water? Where does it go? Well, it floats up to the top. Well, let's take a look at just how much of that ice cube is below the surface and how much is above the surface of the water. Let's imagine that we have an ice cube 3 centimeters on a side. Now, ice has a density of 917 kilograms per cubic meter. Let's imagine we take this ice cube and we put it in some fresh water. Water, remember, has a density of 1,000 kilograms per cubic meter. Well, we notice the density of ice is less than the density of the fluid, so what's it going to do? It's going to rise to the surface. So let's imagine the ice cube comes up to the surface. Let's see if we can figure out how much ice is above the surface, how much is below the surface. Now, let's just keep in mind, if this is 3 centimeters on a side, 3 by 3 by 3, that's a total volume of 27 cubic centimeters. Okay, we'll come back to that. So, let's put everything in SI units. So the volume will be 0.0300 cubed, or 2.7 times 10 to the minus 5 cubic meters. That's the same as 27 cubic centimeters. Now, what's the mass of the ice? The mass of the ice, we know, is the density of ice times the volume of the ice. Well, the density of the ice, we said it was 917 kilograms per cubic meter, times the volume, which we calculated to be 2.70 times 10 to the minus 5, to give us a mass of 2.48 times 10 to the minus 2 kilograms. So what's the weight of the ice? Well, weight is mg. We take the mass, multiply by g, and we get 0.243 newtons. Now, let's think about what are the forces acting on the ice. Well, the only ones we have to worry about are the weight of the ice, pulling it down, and the buoyant force from the water, pushing it up. Now, we know the ice will go to the surface and eventually stop moving when those forces are equal to each other. So we must have that the weight of the ice pulling down is exactly balanced by the buoyant force from the water pushing up. Now, actually, there's another buoyant force due to the air. The air is another fluid, but we'll ignore that. That one is pretty small compared to the force due to the ice, so we won't worry about that one. So we'll equate the buoyant force from the water must be equal to the weight of the ice. So the weight of the ice, the 0.243 newtons, that must be equal to the buoyant force from the water. And we know that the buoyant force from a fluid is equal to the weight of the displaced fluid. Well, the weight of the displaced fluid must be the mass of the displaced fluid times g. So dividing by g, we get the mass of the displaced fluid was the same as the mass of the original ice, 2.48 times 10 to the minus 2 kilograms. Now that must be the density of the fluid times the volume of the displaced fluid. Now notice in this case, because part of the ice is above the surface, it's only that part of the ice below the surface that's displacing the fluid. So, the volume of displaced fluid will be the mass of the displaced fluid divided by the density of the fluid, which is 2.48 times 10 to the minus 2 kilograms, and the density of the fluid is just the density of the water, 1,000, 1.00 times 10 to the 3 kilograms per cubic meter. which leaves us with a volume of displaced fluid of 2.48 times 10 to the minus 5 cubic meters. In other words, 24.8 cubic centimeters. That's the volume of ice below the surface. The volume of ice above the surface is just the total volume minus the volume below. In other words, 27 minus 24.8, or 2.2 cubic centimeters. So we've got, out of the total of 27 cubic centimeters, we've got 24.8 below the surface, which corresponds to about 92% of the entire volume, and 2.2 cubic centimeters above the surface, which corresponds to about 8% of the total amount. Excellent. Now, just one more little side note. Perhaps you've heard about what happens if you see an iceberg floating in the ocean. They say that about 90% is below the surface and about 10% is above. Well, if we were to put this in salt water, ocean water, that ocean water has a density that's even larger than fresh water, which means that's going to push the ice up even further, which might increase the 8% to say about 10%, decrease the 92 to about 90%. So there we go. That's why they say that icebergs are about 90% below the surface, only 10% above. And it comes about because of the buoyant force acting on the iceberg from the ocean, pushing it up. Very, very good. Excellent. Well, that's all for today. I hope to see you next time.